Hello students, welcome to lecture 43 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on hyperbolic metamaterials for nanoscale optical cavities. So, here is the lecture outline. We will have the final design confirmation of the spherical hyperlens that we discussed in the previous lecture. Then we will discuss about the fabrication methods of hyperlens devices, and then we will see how hyperbolic metamaterials can be used for nanoscale optical cavities. So, in doing that, we will first introduce optical cavity and the issue of diffraction limit there, and we will discuss the current state of the art for improvement of the figure of merit of these cavities. So, the spherical hyperlens we have seen earlier as well in the previous lecture. So, this basically consists of a hemisphere geometry, and just to recap, this is composed in this particular application of alternating silver and Ti3O5, that is titanium oxide layers. Okay. Now, this is the schematic that shows this final design of this hemispherical hyperlens, which has got subdiffraction features on the top layer, okay, and then you have TM light excitation from the top. Now, the things to remember here is that you need to ensure that the layer thickness that you are using for making the hyperlens should be much smaller than the wavelength of the incident light. Okay. In doing so, you will be able to use effective permittivity. Okay. So, you can describe the effective permittivity along the radial direction, that is normal to this metal dielectric interface. So, these are like metal and dielectric. The light color one is the metal, the dark color one shows the dielectric here. Okay. This is the wave vector. Okay. That is the sub wavelength feature. Okay. So, this is the interface. So, this is the radial direction. So, you can see Kr, which is marked here. This is basically k theta, and the k phi basically goes inside, right. So, these are typically the spherical coordinate conventions. So, what you see in the radial direction, okay, the permittivity epsilon r can be written as 2 epsilon Ag times epsilon Ti3O5 divided by epsilon Ag plus epsilon Ti3O5. In the tangential direction, that is along the theta and also in the phi direction, you will see that the permittivity is basically the average of the two, okay, because that is along the metal dielectric interface. So, you can write it as epsilon Ag plus epsilon Ti3O5 divided by 2. Okay. So, this is done in the spherical coordinate system. Now, the key properties in this particular design of spherical hyperlens is that you need a small positive epsilon theta and you require a large negative epsilon r, so that you get this kind of a flat hyperbolic isofrequency contour, right. Now, why it is important? Because you want this kind of hyperbolic dispersion curve that basically supports much larger spatial frequencies, or you can say large k vectors than normally the other natural material can support. Okay. So, if you talk in terms of the mode behavior, you will see that the transverse magnetic or the TM waves are basically governed by this flat hyperbolic isofrequency contours, and they allow propagation of sub-wavelength features. Okay. So, this is the trick here. So, you allow the propagation of the sub-wavelength features by supporting the high wave vector, and then gradually you also magnify it in the radial direction, and then at certain point when the feature is no longer diffraction limited, you can simply couple it to the normal wave vectors that allows far field propagation. Okay. So, that is how you are actually capturing the evanescent waves, allowing them to propagate and then convert it into the free space propagating waves. In the case of transverse selective, okay, or TE waves, you will see that there is no electric field in the radial direction. So, it behaves as if it is in a low index isotropic medium, and that allows non-zero spatial frequencies to get filtered out. That means propagation for TE mode is not allowed. That is why we have only shown that initial slide for only TM waves. Now, the magnification directionality depends for in this case for the linear polarized light, magnification will occur only in one direction, okay, that is for the TM supported modes or in the TM direction. So, when you are using unpolarized light that contains TM components spanning the full 2D reciprocal space, and thus it will support sub-wavelength propagation in both dimensions. So, what is the magnification mechanism? As we have discussed, that we are using spherical geometry and flat dispersion profile in that isofrequency contour that will allow gradual magnification of the sub-wavelength objects during the radial direction, because the radiuses keep on increasing. So, you will see the magnification in that direction. Also, there will be adiabatic transformation of evanescent waves into propagating waves. So, that is where finally, you will be able to use your regular optics or microscope to pick up those particular waves and see those diffraction limited objects. So, what is the final result in this case? You are getting a magnified image that is coming out of the plane of the hyperlens, and this image can be captured using conventional optical microscope, because we have already coupled the evanescent wave information and converted into a propagating wave information. So, now let us look into the fabrication of hyperlens devices. Hyperlens fabrication process typically involves the following steps: substrate preparation first, okay, and then you do the deposition to make a etching on the mask pattern. After that, you do the third step, which is basically wet etching process that creates this particular shape, and then you remove this mask. Okay. So, that is done by using chromium etchant, and then you do multilayer deposition. Okay. Here you can consider silver and TiO2 as the two alternating layers, okay, and then finally you make a small dimension, or you can a small intrusion as the object, and then you can set up the imaging system here, okay, and then you can do the imaging process. So, if you go to the details of each of this process, the first thing starts with substrate preparation, as you have seen already. So, first you need to take a highly refined quartz wafer. So, you use a wafer with 500 micron thickness for this fabrication process, and then you spin coat the wafer. So, this is basically a rotating platform on top of the substrate is put. So, you put a precursor solution, and then you apply a photoresist at 2000 rpm, and then you bake it for 60 seconds at 90° centigrade. So, that way you will be able to make a layer of photoresist that can protect the wafer from damage during the cutting. And then finally, you do the cutting. Okay. So, you use a dicing machine to cut the wafer along with the photoresist into 20 mm by 20 mm pieces. Okay. So, once done, then you remove the particulates. So, you blow the pieces using compressed nitrogen gas, a nitrogen gun, okay, and the cleaning process involves placing of those samples into an ultrasonic bath with deionized water for around 5 minutes at 48° centigrade, okay, and that removes the photoresist layer using the ultrasonic bath, but this time in acetone for 5 minutes and at the same temperature 48° centigrade. So, finally, you clean the substrate with two ultrasonic baths. One is acetone for 5 minutes at 48°, and then you take isopropyl alcohol for 5 minutes at 48° centigrade. So, the final step would be to dry the substrate using a compressed nitrogen gun. So, that is how your substrate gets ready. Next step would be to etch the mask pattern, right. So, for that you load the quartz substrate. So, you have to place the clean quartz substrate in a high vacuum electron beam deposition system, okay, and you have to ensure that the column rotation is enabled. So, there you got to deposit chromium, okay, as you can see in this figure. So, the deposition rate is typically 2 Armstrong per second, and you need to deposit at least 100 nanometer thickness. So, you can prevent pinholes, during later etching steps. And after that you prepare for the milling process, that is focused ion beam kind of milling process. So, for that you need to vent the chamber, okay. You mount the sample on this focused ion beam holder using some conducting copper tape. Then you load the FIB holder into this FIB chamber, and you close the chamber door and use the pump to evacuate the chamber again. After that you turn on the ion beam. So, under the beam control you select beam on. So, and once you set the ion beam current around 7.7 picoampere and acceleration voltage around 30 kV, okay, that time you can turn on the electron beam and focus the image at low magnification using software. So, you got to set the working distance to 4 mm in this SEM mode, and you tilt the holder to 52 degrees and capture the SEM image at various magnifications before doing the patterning. So, under the patterning what you have to do, you got to select the region first, okay. For that you can consider fabricating a 50 nanometer hole array on the chromium, okay, as you can see here, and then you can use simple tools or import bitmaps or scripts for any kind of complex structure. So, here it is hole, so it is simple. So, if it is a complex structure you can make that pattern using scripts or by importing the bitmaps. So, after the patterning is done, you got to turn off the electron and the ion beams and let the system cool down. You vent the chamber with nitrogen gas and remove the holder, and finally you close the chamber and re-evacuate by pressing the pump button, right. So, with that your sample is ready for etching. So, next step will be the wet etching process. So, you are doing the wet etching of the quartz, right. So, you got to place the pattern substrate into a 1:10 buffered oxide etchant for around 5 minutes, okay. So, you will see that quartz is selectively and isotropically wet etched. So, that will form a spherical shape, and the lens shape is determined by this mask, okay, and the diameter basically controls the etching time, right. So, a smaller pattern diameter basically yields a better spherical shape. So, you will see, for example, a 1.5 micron diameter hemisphere forms within 5 minutes time, right. So, after doing that you got to rinse the substrate. So, you place the substrate in deionized water to clean off the buffered oxide etchant. So, you have to do it 5 minutes per rinse and you repeat this step twice, okay. So, one thing to remember here is that this buffered oxide agents are hazardous. So, you got to carefully handle the sample. Next step would be to dry the substrate. So, you can dry the substrate using compressed nitrogen gas, okay, and finally you remove the mask layer because your formation of the hemispherical well is done, okay. So, you remove the chromium mask. So, for that you immerse it in CR7 chromium etchant that will remove your chromium mask layer, okay. So, you got rid of the mask, okay. So, after this step you will see a 1.5 micron spherical pattern substrate that is remaining with you, and the final cleaning will be done again with deionized water, for 5 minutes, and after that you have your substrate ready for multilayer deposition, right. So, in this process you will deposit alternating layers of silver and TiO2. So, in this case we are considering each to be of the same thickness, okay, 15 nanometer, okay, and on the spherical quartz substrate. And also this is the reason why in the initial slides, if you see that the volume fraction was not mentioned and it was taken as half, if you see in this particular case. Okay. Here also the metal and the dielectric layer thicknesses were considered to be same. Okay. So, what is the growth rate? The growth rate is typically 1 angstrom per second, and this slow growth rate basically ensures uniform surface roughness. So, the process step involves, first you have to press the vent button of the electron beam evaporation system, and you have to wait for the venting to be done. Then you load the patterned substrate into the system, you close the chamber and evacuate it to 10 to the minus 7 torr vacuum, and that will minimize surface scattering. And then you deposit a 15 nanometer silver layer at the deposition rate of 1 angstrom per second. Let the substrate cool down for 5 minutes, and then you switch to TiO2 crucible, and with that you deposit a 15 nanometer TiO2 layer at 1 angstrom per second again. So, with the time you can basically calibrate the thickness that is getting deposited. Let the substrate cool down for another 5 minutes, and in this way you can repeat the silver TiO2 layering for multiple cycles, and that will allow you to build this multi-layer hyperlens. Now, the final thing will be the fabrication of the test feature for this hyperlens imaging. So, after the multi-layer deposition is done, sub-wavelength features can be fabricated for testing. So, you switch crucible and deposit a chromium layer of 50 nanometer thickness on the hyperlens for patterning. So, after the chromium deposition, you turn off the electron beam evaporation system, you vent the chamber using nitrogen gas, okay, and then you open the chamber door, remove the mount holder, and you strip off the fabricated hyperlens device. Okay. So, after that you close the chamber again and evacuate, close the chamber door, you evacuate again by pressing the pump button. Okay. So, finally you mount the chromium coated hyperlens into FIB milling system. So, that is where exactly you inscribe those nanometer sized apertures or slits as your test features that you will be used for hyperlens imaging, right. So, with that we understood how a hyperlens is fabricated. Okay. Now, let us look into some other applications of hyperlens, or you can say hyperbolic metamaterials in general, for nanoscale optical cavities. So, these are basically optical cavities, and we will see how diffraction limit issue is troubling them to give you a higher figure of the merit. So, normally you will see metamaterials can offer several solutions to overcome diffraction limit issue. So, the first thing is that hyperlens technology could demonstrate super resolution imaging, and that we understood well by now, that it enables high K vector to propagate light and then take it into far field. So, this unique ability of hyperbolic metamaterials allow one to access the sub wavelength light, which are typically the evanescent waves, okay, and also supports other application beyond imaging. So, this is what we will be seeing today, that other than imaging also we can use this for other applications. Okay. So, right now we will discuss that how this kind of metamaterials can be used to overcome the current limitations in the state of the art optical cavities. Okay. So, optical cavity basically tells you it is a cavity. So, there are two mirrors on two ends, That is a typical optical Fabry-Pérot cavity, right. So, what it does, it basically confines light between two mirrors, and upon multiple rounds of reflection, it enhances the energy to finally generate a laser beam, right. So, a cavity is formed between two mirrors, and the light gets reflected between them until it is completely absorbed within the medium or at the mirrors. So, this is showing you different modes. So, this is m equals 1, m equals 2 and m equals 3. 3 different modes are basically shown here. So, while reflecting, what happens, the energy level basically increases, and it can become unstable. So, when the energy becomes high enough, an external force can trigger light emission as a laser beam, okay, and that will allow the energy to return to the ground state. So, here the goal is to capture the light efficiently in the cavity, increase the energy levels with minimal loss, and then finally generate a laser beam with less external pump force. Okay. So, the resonance condition for the standing waves that we just saw can be written as Fm equals m by 2L times C by n. What is m is basically the mode order. So, we have seen m equals 1, 2 and 3. So, Fm will be the frequency corresponding to each mode, and you can see that that is inversely proportional to the length of the cavity, okay, and the refractive index of the medium, right. So, the resonance frequency, if you want to tune it, you can simply adjust the length of the cavity or the refractive index of the cavity medium, right. Also, if you see that if m increases, that the mode number increases, you will get higher frequencies, right. So, that will basically correspond to, on the other hand, you can say higher mode causes higher frequencies and shorter wavelength, and that will correspond to smaller refractive index. So, in conventional cavities, size L and index n are basically independent to each other. So, by squeezing light into smaller dimension, it basically increases the photonic density of states due to reduced mode volume. Okay. So, what happens in this case, it will lead to much faster emission process that will enable brighter and faster optical emission, right. So, this particular independence is something that will be different in the case of metamaterial based cavities, which we will be discussing later. Okay. So, we will see here first that this kind of enhancement of emission can be quantified by Purcell factor that compares the tailored photonic density of states of an emitter in a vacuum. Okay. So, the high quality factor cavity basically allows you to enhance the photonic density of states, okay, that is achieved by narrowing the spectral line width rather than shrinking the mode volume. So, researchers typically introduce a high quality factor cavity to enhance the photonic density of states, and as I mentioned, it is done typically by narrowing the spectral width or spectral line width rather than reducing the volume of the modes. For optical cavity, an important parameter is the quality factor, that is basically defined as Q equals 2 pi into the electromagnetic energy stored divided by the energy dissipated per cycle, right. So, it basically indicates the optical loss, that means it tells you how long the optical energy can be stored in the resonant cavity. Okay. Another important parameter is the modal volume, okay, that is defined as V equals total electromagnetic energy divided the maximum electromagnetic energy density. So, that tells you about the modal volume, and this gives you the indication of the size of the optical confinement, that means how tightly the optical energy can be localized. So, Q by V ratio, okay. So, when you have a large Q by V, that means you have low loss and small size, right. So, that is a good thing because it also represents long photon lifetime and strong optical intensity, and therefore you can use Q by V as the figure of merit for the enhancement of light matter interaction, right. So, this is a better figure of merit that could quantify the enhancement in light matter interaction, right. So, we will basically now compare couple of different cavities and see their performance in terms of Q by V. So, this is our figure of merit, okay, for the discussion. So, we can start with silica microspheres and microtoroids. So, you can see they have very high Q, okay. So, they basically have the highest Q, so is of the order of 10 to the power 8, okay, but the volume also is very large, and they also have the largest, you can say the modal volume, that is given in terms of 2000 lambda by n cube, right. So, that tells you that the Q by V ratio is not that large, okay. So, if you use high index material like silicon, okay, in that case you can bring down the modal volume, okay. So, that allows you to fabricate smaller micro discs and micro ring resonators. So, you can see here the quality factor and the modal volume that also reduces. So, overall you can get some improvement in the Q by V ratio. You can also look into the photonic crystal cavities. So, there you can achieve very little modal volume. So, the volume is of the order of almost a wavelength, okay, 1.4 lambda by n whole cube, and this is the quality factor, okay. So, the Q by V ratio is pretty good here. So, however, it is still diffraction limited, because you cannot further reduce the mode volume, okay, below, and you cannot go sub wavelength. Then you can move towards plasmonic cavities, where you can think of plasmonic microdiscs or Fabry-Pérot cavity kind of nanostructures. There you can achieve sub wavelength mode volume. So, you can see V is very small, okay, 0.04 lambda cube. So, that is like you can achieve sub wavelength modal volume. So, although your Q quality factor is not good in this case because of the loss inherent to plasmonic metal, okay, here you can still appreciate that the Q by V ratio is pretty high, okay. However, the overall performance in this case is also limited, because Q itself is too small to match any kind of conventional dielectric cavities. So, finally, you can see that metamaterials can provide a solution here. You can think of hyperbolic metamaterials to give you cavity which can overcome the size issue, that is the diffraction limit issue. So, you can go very sub wavelength or deep sub wavelength. So, volume can be 0.0002 lambda cube, and the quality factor is around 20. So, you can have significantly high Q by V ratio, okay, using this kind of metamaterial concept, okay. So, that also allows sub wavelength confinement. So, with that we will conclude this lecture. We will continue the discussion of this hyperbolic metamaterials for optical cavities in the next lecture. If you have got any query regarding this lecture, you can drop an email to this particular email address. Thank you.